Hi, I'm Brina. I'm the team lead of Wichita State Launch.
Hi, I'm Meg. I'm the controls and stability lead.
Hi, I'm Adit. I'm the structures team lead.
Hi, I'm Lucas. I'm the safety officer and propulsion lead.
So we're Wichita State Launch, and we were really excited about competing for the first time this year in Huntsville, Alabama, as a part of the NASA Student Launch Competition. Given all of the recent changes going on in the country with the coronavirus stuff, that was no longer possible. And so one of the things that we were most excited about with the launch was being able to learn about the things that the other teams were spent their time on and were building throughout the year, both with their rocket vehicle and with their payload. So since we weren't able to do that anymore, we were trying to come up with some way to still share in the accomplishments of the other teams as well. And so, yeah, that's what brings us here.
So as Brina mentioned, we decided to come up with like video system, and since everybody's using Zoom now, we were like, we should invite other teams to have like a little bit of an informal interview where both the teams present their rockets and their payload, and we talk about the design process and this whole experience like we would have done if we were actually in Huntsville.
All right, as Meg mentioned it, so that's an idea. We need a name. So we have decided to call this a launch hour. So what we'll do is kind of talk to other teams on the Zoom meetings and present our rocket, what's going on, what's the design look like. Same way, the vice versa, they will present us. We will have some questions, and then we will post this. We will record this whole video with everyone's consent, and then we'll post this once a week or twice a week as per the availabilities and how we conduct the meetings.
All right, so yeah, I got to intern at NASA Ames this past summer, and I got to meet some really cool people. And so our first guest is my desk mate and co-intern, Holly, and she's on the Oregon State rocketry team competing in USLI this year too. So they are our first guest. She reached out to me last week, and we were both excited to share about our projects and learn from each other. So they're our first guests, and we can start hearing from them now.
Tell us about your team and kind of like what your team makeup is and why you guys are excited about the project and things like that.
All right. So just from the capstone side, we have 18 different capstone members split across 4 different majors. Majors are mechanical engineering, where that's where we have most of our capstone members coming from. And then we have electrical and computer engineers, we have computer scientists, and we have 1 education major, so that we have a pretty even delineation and spread of our team. We also have approximately 10 different volunteers on our team that are split throughout the different sub-teams. Our sub-teams from the technical side are broken into air recovery, structures, propulsion, and payload. And then within those, we also have like CS for payload and CS for air recovery and ECEs for payload and air recovery. And then we also have more of the soft skills sub-teams, which are like budget and finance. We also have documentation experts because USLI has a ton of documentation. We have STEM engagement, and we also have safety. And so we have a lot of different opportunities for people to get involved. We also have different sub-teams or like smaller subset projects for our underclassmen volunteers so that they can get really involved, like helping us design and build different test stands. One of our groups of underclassmen built and designed our black powder ejection test stand for us. And that was a great project to keep them involved as well. So that's basically the breakdown of our team. We're excited and we love USLI because it's a NASA-based competition, and while there are several other ones, this is really awesome because we get to launch a rocket and basically go through an entire design and build process of NASA, or that mimics NASA very similarly. And so we also get to have a rocket and we get to have a payload, which is a unique thing for many of the rocket teams and many of the rocket competitions out there, because if there is a payload, it's generally a scientific payload as opposed to one that actually goes out and does something. So that's why we really like this competition.
Okay, perfect. I'm just gonna start going over things then. So our overview is, obviously we launch, we hit motor burnout, we then coast to apogee, where we have our first event. Our rocket has one main and one drogue parachute. Everything comes down under one tether. And with our apogee altitude, we're shooting for 4,000 feet, and then our main parachute deploys at 600 with their backup charge at 500 feet. And then we land, and we have a rover that goes off and does the sampling and collection. Overview of our launch vehicle: 119 inches in length and 60.9 pounds in weight, with an inner diameter of 6¼ inches. I'm not sure if those dimensions are 100% correct. They might have changed a little bit. Our payload is a rover. It weighs 6½ pounds. I think that's with its retention system, which is shown in this picture as well. Skip all of those numbers. So then I'll go over air and recovery. Our stability is 2.62 and then increases to 3.19 with our mass distribution. Our mass distribution being like this. So we have our nose cone, which holds our avionics. Right behind the nose cone, we have our payload. Right behind our payload, we have our main parachute. And then we have our coupler with our altimeters. And then after the coupler, we have our drogue parachute. After that, we have our air brake system. And then after that, our motor. Our air brake system was a rack and pinion design driven by a servo. It reads active altitude and acceleration data, and then it uses that to actively calculate our predicted altitude, and then will extend the blades if it thinks it's more than 66 feet over 4,000, which is how it was intended to fly. We never got to fly active though, unfortunately. Our parachutes, we have a 12-foot main toroidal parachute and a 36-inch X-form drogue parachute. Our recovery harness for our main parachute is like this, and it's pretty much the same for our drogue. Like I said, everything's tethered together. So we have quick links attached to bulkheads in the fore body tube and in the coupler, with a zipper, or a tether in between those two with quick links connecting them to the eye bolts on the bulkheads. And then we tie off another shock cord and then connect the parachute to that. Pretty much same for the drogue. It just has a bit larger of a shock cord for the tether. One interesting system we're adding into our rocket for competition that unfortunately never flew active either, but Amy designed a backup black powder charge retention system, because our backup charges were oftentimes, after our main charge would eject our parachutes, our backup charges would then come out of the airframe in the air and then cauterize our parachute. And so what this system would do is retain our black powder, our secondary black powder charge within the rocket, and then it would detonate that charge within the airframe no matter what. So it wasn't dangling in the air, and the charge wasn't cauterizing our parachutes. I guess that's pretty much it for air and recovery. Do you guys want to hear about avionics? I don't really know how much I can talk on that. That's more of our ECs.
Whatever you want to talk about.
Okay, I don't have much to say about avionics, so we will move on to structures and propulsion.
All right, I think I unmuted myself.
Yeah.
All right, cool. So structures and propulsion. Can we go to the next slide? I'm Nathan, by the way. I did a lot of the structures stuff, helped out with that. So an overview, we have a nose cone. Inside our nose cone is our main tracking for the launch, the rocket. That was independent of our recovery electronics. We just had tracking, GPS, and data taking, so we could like record altitude and stuff. Right after that, in the fore section, we have our our rover bay, where our rover is retained, connected to a single bulkhead that's in the middle of our 4-section airframe tube. And then right after that is the main parachute bay. And then we have a coupler that's tethering our fore and aft sections together. Inside the couplers are main recovery electronics, which will eject our main and drogue parachute. Right after that, in the aft sections, our drogue parachute compartment, then our blade extending apogee variant system compartment, and then the motor bay and the fins. Can we go to the next slide? There's some pictures of us manufacturing. There's pictures. So for the aft section, it's completely carbon fiber for the most part, the airframe tube at least. The fins are a composite, are epoxy to it through wall style. So we have fin slots cut out, the fins are placed in there, and then epoxy to the motor tube, and then large epoxy fillets because we had a lot of room because our motor was small relative to the size of the airframe, so we didn't have to do any fancier methods of attaching the fins, and this made sure they were very, very secure and weren't going to break off or anything. The fins themselves are a composite sandwich of carbon fiber with a G10 core. There's a good picture of it, with and a Nomex honeycomb that we laid up and cured. The fore section is not carbon fiber. The fore section and the nose cone are both fiberglass. Sorry, I'm jumping around to which the slides are on. So yeah, so our fore section is completely fiberglass because we need to be able to talk to the ejection system for the rover, and we need to be able to talk to the tracking and the avionics there in the nose cone. Yeah, we actually had to repurpose a section for our fore section because our originally the tube that we ordered, the company that was making it had some issues, so we have to use a legacy tube and repurpose it. We can go down to the aft parachute mounts. So the aft parachute mounts were an interesting kind of design challenge for us because we needed a way for our blade extending apogee variant system to kind of slide into the airframe and be held in place, but also have a way for the parachutes to attach that is epoxied directly to the airframe. But because we wanted the blades and that system to have as much room as possible, we needed the parachute mounts to be as small as possible. So we ended up milling out aluminum mounts that had an outer diameter that was the inner diameter of the tube. And so we milled out mounts to attach eye bolts to it and increase their surface area, made them as small as possible so we could just epoxy them to the inside of the airframe, and then have the beef system slide in as one complete unit. So you're not working inside of an airframe tube trying to work on small electronics or bolts with the blades and whatnot inside little holes. You just slide the entire thing out, work on it, slide it back in, seal it, and have as much area as possible to do that. This is a picture of, actually there's a picture of our pressure seals right here. So there's a similar one on top of the beeves unit. But this is our, this goes inside of our coupler. So this is our recovery electronics here. And that's essentially just a 3D printed mounting plate that has our RRC3s and batteries on there. And then those are on steel threaded rods. There's 4 of them. And on either side of those threaded rods, we have those sealing bulkheads. So we can, because this whole unit hangs inside the coupler in between the fore and aft section during recovery, because during apogee, the drogue parachute comes out, and then about 500-600 feet, the main parachute deploys. And so this will hang in between there and holds the forces of recovery. So we have to have pretty big steel rods going through it so it doesn't tear itself apart. Next slide. Go to the coupler. So the coupler itself is a fiberglass construction. We made it out of unidirectional fiberglass and laid it up inside an extra piece of airframe we had so that it fit perfectly inside of the airframe. We originally were going to go with carbon fiber, but there were some issues with the original coupler that we laid up out of carbon fiber because the fiberglass mold we had it in and the carbon fiber coupler, because they have different rates of like expansion and contraction when they're heated to cure, they get stuck inside each other. So we had to actually sit there and sand out the carbon fiber coupler for like several hours just to get it out of the mold. And so we ended up just doing one out of fiberglass because we could make the fiberglass strong enough. And there was no reason to destroy our mold if we had to make another one again. As for our nose cone, I don't know if we have any good pictures. Oh, there's some pictures of damage. So our nose cone, because we had a weird diameter of 6.25 inches, we took a very large 7.5 inch, I think it was commercially made nose cone, because we didn't want to have to make our own nose cone, cut it down, and then laid up a coupler inside of that out of fiberglass, which worked pretty well until our first test launch, when it broke free of the airframe and then fell 500 feet onto the ground. And so if you go up to the picture right above that, you can see the damage before we cut it out. Yeah, so we had these big sections where we had some ballast that impacted the sidewall, and so we had to cut out that entire section and patch that, which is ready to be flown but has not been flown yet. That's all I have.
As far as structure slides go.
Yeah, there's not much else. We are using a thrust plate for our motor, and our motor is an L2200, which is kind of the upper end of what we're allowed to use. So we milled out an aluminum thrust plate, and then we're using an aero pack retainer on there to keep the motor in. And then that's a picture of our first launch.
All right, payload.
Payload. Okay, so hey guys, I'm John. You got my hopefully you guys can hear me. I think I muted it. Yeah, go on to the next slide. We have a couple pictures here that we can kind of go over. So this is the payload. We had 4 mechanicals on it, and we kind of broke it into 4 parts: the ejection and retention system, the chassis, which we pretty much what the rover. Sorry, take a step back. So what we decided to do is we tried to use a rover to do the ground mission. So shown there in the middle, you can kind of see the rover that we decided to go with. It has wheels that kind of expand out. Jordan will touch upon that a little bit when we kind of get to those slides. But essentially it collapses and then it can slide into the rocket. So it's a biaxial design, and that's what we were planning on using for the ground mission. And then it kind of slides onto this lead screw, which both ejects and retains it within the airframe. You can kind of see that there. If you have the pictures bigger than the one on mine, it's like arrow 1, 2, point out kind of the ejection system. Next slide, Holly. Thank you. So this is kind of the chassis, or what all the parts of the rover fastened onto. We decided to make it out of plywood because we had some laser cutters that we could use. So one of our freshmen that helped and volunteer actually cut a lot of these for us. And pretty much it's just plywood that's laser cut and kind of presses together with a couple aluminum rods that fasten it all and sandwich it together and hold it as a unit. And then there's some 3D printed parts that hold the electronics and the battery, which you can kind of see there in the black. What's the next slide? Okay, so Jordan, you want to talk about your reinvention of the wheels that you went through?
Sure. So these were designed in an attempt to give the rover more ground clearance so that it won't get high centered as it drove over any uneven terrain. Took full advantage of 3D printers because it was easy to do and strong enough for everything we wanted to do it with. The challenge was to make a wheel that was that could fold against the body and fit inside the rocket, but also be able to fold out and be usable instead of walking on stilts, having a wheel that was actually round. So that's not quite the final design, but pretty close to it. You see the ends of the wheels have 2 radiuses on it, one for rolling and then one to fit against the rocket when folded up inside. Just regular spring hinges, so when it pops out of the rocket, it springs out, and then you kind of walk up onto the wheel and then roll from there. Tank drive, nothing really special there. It has a skid plate made out of carbon fiber in the back, and that, yeah, that's self-explanatory. The couplers connect directly to the motors. We have pretty beefy motors that are secured very well to the chassis, so that really wasn't a concern about damaging the motors or, after some improvements, coming off. Made a couple modifications to the D shaft so the wheels wouldn't come off. But yeah, that's about it for that.
All right, and then how the rover was, we planned for to kind of pick up the ice sample was with a scoop. Kind of see it here with the blue picture on off to the right are some of the pictures of it actually being used. So it's essentially just a little 6-volt motor connected to a all-thread rod, and when it rotates, it kind of pulls down the 3D printed blue thing into the material as rover drives. And the theory was it would hopefully collect the material in that, and then we lift it back up and hold it against the bottom of the chassis. We tested it with some plastic BBs that we had, and supposedly we're supposed to be going through the ground mission before the end of the year, but we'll see how that goes. But that's what the collection system is. Next slide. Okay, so then the ejection and retention system was a little bit more interesting. There's a lot of pictures here that kind of show it all put together. So essentially the rover slides onto that lead screw, and then there's these two wooden bulkheads that thread on either side of the rover, and it kind of sandwiches it in and holds it as a unit. And then when the all thread rod is rotated, it pushes it out slowly. And you can we found out how to make it so we could assemble this all outside of the airframe and then slide it in as one unit. The bottom picture there kind of shows what it looks like before you slide into the airframe, which is pretty cool. It helped with integration a lot, but that's what kind of how it turned out. Essentially what it came down to is the entire rover and system rested on that lead screw, and that's the main way that it was supported. And that was a big problem that we kind of ran into, was all of that weight that it's going to see and flight forces that it's going to see are all held by the connection between that lead screw and the motor that rotates it. You can kind of make it out on the far left in that bottom picture, and then in the top picture is on the other side of that assembly that holds the motor. And pretty much all that rests on one 632, I think, fastener, which was a little bit of a concern, so we beefed it up by putting some more stuff in there. Yeah, but that's kind of how the system goes together. Initially it was threaded on behind the nose cone, but in our first launch, Nathan had some pictures of it, but the nose cone, so we ran into problems where the motor couldn't shear the nose cone off and break all the 3 shear pins. So we found smaller shear pins that we could use, and it was able to push through those. But from the first launch, we found out that the nose cone fell off mid-flight, which was a bit of a problem. We didn't want that happening when we went to competition, so we decided to thread the nose cone onto the lead screw that held the rover. And that you can kind of see that patch job in the top right picture where we added a fastener, or we call them all thread nuts, but it's essentially the nut the all thread rod or the lead screw threads into. But yeah, that's the ejection retention system. Next slide. I think that kind of finishes it off for payload.
Yeah.
Yeah, that's we did some testing, and then there's some pictures of our first launch underneath that slide, and that, like, all we found out was it survived despite the nose cone falling off, which was good. And
rover stayed inside. It's kind of funny.
Yeah, the rover stayed inside. That was a good thing. And the only damage we could find was on that motor assembly that connects to the lead screw. The bulkhead that all that it fastens to had some wear on the inside, but yeah, it survived. It didn't exactly work when it came out, but we did some things to fix that, and we're planning on launching it, but we haven't actually done the payload test demonstration flight. So that's where it is. I think we're going on. I don't know who's talking next.
That's it. The rest is just payload electronics and safety.
Yeah, so payload electronics, it has a very big battery, and we control it with radio controllers, and it has a camera that may or may not work. I think that's as much as I can talk about. Very large battery. That's all I know.
I was wondering how the air brake. Sorry, Lucas, I just cut you off.
No, go ahead. You're good.
I was wondering how the air brake system works, like the mechanical design of it.
Yeah, so it's a rack and pinion design, and I guess it doesn't really show in this picture. Let me go to CDR. I think I have a better picture in CDR, but there's a servo that attaches to a plate with the gear on it, and yeah, just drives the plate that the gear sits on. The gear is actually welded to it. CDR. So here's a better picture of the entire system. So on the top, so there's 4 wooden bulkheads. On the top, we have our ballast bay, because that's kind of part of our, we called it an apogee variant system. So that includes ballast and the active air brake system. And then in the middle, we have our blades. And then below that, we have the servo motor and the mess of electronics that go with it. So it has a LiPo battery, and then it has an acceleration and an altitude barometric pressure sensor. Sorry. Yeah. To answer your question, I have a video of it somewhere too. Yeah.
So your guys had 2 blades, correct?
Yeah, so because we had to slide past the parachute mounts, it was originally designed to have 4 blades, but there was just no way to fit 2 blades on like the shorter ends. So it was just 2.
Okay, so all of those are like springs, like once they go out, it like springs out, right?
Oh yeah,
Yes.
like train, yeah.
So once they spring out, do they lock in that position?
They overextend past vertical. So in theory, the weight of and then in testing, the weight of the rover was enough just to keep them open.
Oh, okay. Huh.
Does the whole, like, I guess, chassis system, does that rotate with the rover as it moves, or does it stay like upright?
Just out of view is the tail that keeps it upright. So when it spins, there's a tail off to this side. Yeah, there's the tail.
It's insanely blurred to bring down the image size, but yeah, it shows a little bit.
Yeah, the video is running forward and back, so it doesn't quite give.
Oh, sorry. Okay, here we go.
Yeah, that's cool.
That's pretty cool.
Yeah.
What kind of microcontroller did you guys have on the rover?
Honestly, I don't know. We the electrical engineers made their own PCB, custom PCB that controlled it all, and then we had a legacy motor controller that they made last year to power the motors.
Oh, that's pretty cool.
So you guys were able to launch one time, like with the full scale rocket?
Yeah, 1 full scale, and then I think 1 launch got canceled before we got out to our launch site, and then we had to scrap our last launch because it was snowing and the ceiling was too low.
So on your first test launch that you did for the full scale, what was your apogee like?
One was an average of 4,456 feet between our 2 altimeters and then our custom avionics that our ECEs made.
Okay.
So why did you choose 4,000?
I think we were just at a meeting over like, what altitude do we want? And someone said 4,000 and the rest was like, okay. But
Nice.
it's last year we had we chose 4,500 and all of our components are really heavy and we had to cut weight like the entire time. So it's easier to shoot for a lower altitude and add weight than it is to cut weight. So, yeah.
Good advice. So can you talk a little bit about how you guys, like your different teams work together? So like, would the vehicle team say, hey, payload, you guys are limited to 10 pounds or 20 pounds or whatever? Or is the payload team more kind of setting that limit for itself? So since we are so small, like we're basically all on every team.
Yeah.
But like, so I'm interested to hear about how that worked with you guys since you're a lot larger.
Does anyone want to answer that specifically?
Yeah, sure. So I feel like payload was kind of in the middle of it because everything is designed around the payload, like the rocket, the motor we use and the size of the rocket and all that. So payload had a lot of people ask questions about what we're doing. And kind of how it turned out is we have weekly meetings with the entire team. So out of those, there was usually some discussion between, like each team has a team lead. So there's some discussion between the payload team and other team leads kind of about like, hey, this is what we're planning on doing. This is how it's going to look. This is how the weight's going to be. And then there was random kind of throughout the week meetings whenever we saw each other in like either the shop where we're making it or kind of in the computer lab where we just kind of saw each other and we discussed like, hey, this is what is, or these are the problems we're having. And like, oh, it's going to be this big instead of this big. And figured it out that way.
Okay.
I think originally we kind of went together and like towards the beginning of this whole thing, and we have our simulations on Open Rocket, and we just threw all our estimations in there, and we're like, all right, with this weight, we're getting to this apogee, and we're going to need somewhere around this motor. And then from there, it was just making sure we communicate like, hey, we finished this part of the rocket, and it weighs this much now. Here's our apogee with the updated simulations, stuff like that.
First off, payload has a lot of cool pictures of it in our presentations, which is awesome. But it's, unique thing about it. It's kind of the expandable, the wheels that expand. It gives it a little bit of character because they're not locked in place. So when it drives around, they kind of collapse and expand. So it kind of drives a little bit more rugged, which is fun to watch. It also is orange and black and has a beaver tail, which is pretty sweet since we're the beavers. But that's kind of the unique aspect about the rover. I mean, it's still a rover, which is pretty standard. So I guess that's what I'll say about the payload. Nathan, you want to talk about the rocket?
Yeah, so I think just the overall, like the design overall is pretty like simple. It makes it really easy to kind of modify and change things when you need to, and there's so much in there that can be like just pulled out and changed whenever you want. Like the like mounting points for hardware can just be changed. You just slide out the plate and slide a new one in and you're good to go. And just keeping it overall pretty simple and easy to work on, relatively sometimes.
I actually do have a question. So you guys manufacture a lot of your own parts. I was wondering if your team had always done that, because I think part of the difference is because we're so small, we buy most of our parts commercially. But I was wondering if you guys do it more for the experience of it, or if you see like a really distinct advantage to doing it on your own.
So for a lot of the manufacturing stuff, I think there's a really good opportunity for experience making your own parts and kind of learning what goes into making lightweight, strong components for an aero vehicle versus like you can always look up on a data sheet and buy them. But when you sit down and start like with a layup for a fin, or like, all right, what orientations do I need? What weave do I need? I think it's really helpful. Another reason is because we were able to get a lot of those materials very cheaply for us because we're lucky enough to have other teams that are using composites and machining. And so we had a machine shop right next to where we built the rocket. We had a composites lab 10 feet away, and we have a SAE team that works out of the same space. And so we were actually able to borrow a lot of the materials. So it's actually probably cheaper for us to manufacture all the stuff ourselves, minus our airframe.
And then the last question I have is, do you guys have like some advice you would give to either like a future SLI team at your school, or just people or college students who would be interested in this project in general?
USLI is a really fun project. You learn a lot and it's a ton of fun. And I think if you have the opportunity, you should do it.
So that was Oregon State. So we were really happy to hear from them and learn all about their rocket design. And so yeah, we're gonna try to do this about 1 to 2 times a week. If you guys like learning about these sorts of things, feel free to leave us a comment, or if you have any other ideas for things that we can, questions we can ask the other teams, or any sort of ideas you have to make this sort of little video segment go better, we would love that. And yeah, we're gonna see you guys next time. Bye.
Bye.
Bye.